So this is the study guide for the for exam 3 for organic 1 in the spring of 2016, although it's probably not that much different than what we've been doing before. So with that, so these are some of the questions that you'll see as far as part of the free answer portion of that. So so one of the things we're going to do is ask you to calculate the degree of unsaturation, which I'll give you this part of the equation on the exam. I'm not going to give you the key, but for that, but you're going to need to know how to use it. Okay, so with that, so we have carbons, nitrogens. The X is any type of halide, something like that. So and number of hydrogens. Okay, so DOU. All right, so in this case, DOU. Right, 2 times the number of carbons here is 6 plus 2. There's no nitrogens. However, there are 2 bromines. Okay, so minus 2 minus number of hydrogens 10. All of that divided by 2. Okay, so with that, so let's see. That's 12, 14. 14 minus 12, right? 2. So 2 over 2, 1. Okay, so that means that in this formula there's either 1 ring or 1 double bond. Stuff like that. So, okay. So here, again, we're going to use that formula. 2 times the number of carbons, so this times 5 plus 2. Plus the number, there's 2 nitrogens, right? There aren't any halides, and there's 8 hydrogens. Okay, so 10 plus 12 plus 14, 14 minus 8 divided by 2, right? So this would be 6 over 2, right? So this would be equal to 3. Okay, notice that oxygens aren't part of this formula, so we just ignore them, right? They're not part of the formula, don't add them in. Stuff like that. Students try to do that, and they get the answer wrong. Also, this is always going to be a whole number. You're never going to have a half a double bond, right? So with that. So if you do this calculation and you get a half, you get 2.5. You don't get a whole number. Recheck your calculations. Okay. So there you go. Next up, we're going to be naming alkenes and alkynes. Now, with the alkenes, you're going to want to include the cis and trans. This will be in there in the instructions for the problem. Okay. So with that, so first off, right? Let's go do this one here. You can always draw in the carbons, right? Put in your dots. Okay. So remember the main chain has to include that. The double bond in here, right? So here we go. So 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Go up and down. Well, it's looking like that is our main chain, right? So, okay, so the main chain. I'm gonna do this here. 1, 2, 3, 4, 5, 6, right? So C6, right? Which would normally be hexane, right? But for the alkanes, or excuse me, for the alkenes, right? We take off the A and E and add E and E. Okay, so it's going to be a hexene. Now, for the side chains, right, we're going to have to figure out where that double bond starts, right? So I always write alkene here, right, for the numbering. But then there's also this ethyl group here, so ethyl. Okay, so then the number 1 is going to start on the end closest to that double bond, right? So it's going to be here. So it's 1, 2, 3, 4, 5, 6, right? So the alkene starts at carbon 2, and the ethyl starts at carbon 4. Okay, so this would be 4 ethyl, 2 hexene. Okay, but since it's an alkene, right, we have to say is it the cis or trans configuration, right? So you can always draw in the hydrogens, right? And notice how they're both on the same side. That means that they're cis. Okay, so here's your name, right? We have a main chain that's 6 long, right? And we have a double bond in it, right? So 6 long, right? So we have a double bond in it. That's what the ene means. Where does it start? It starts at carbon 2, right? So with that, and it's in the cis configuration here, right? Hydrogen's on the right, on the same side. Okay. We also have an ethyl group, right? Where is it connected? It's connected at carbon 2. So there you go. Okay, now for this one, right? Again, you can draw in the carbons. Okay, now remember, right, with the alkyne here, right, it has to include that on the main chain, right? So 1, 2, 3, 4, 5, 6, 7, 8. Right? Don't forget to go down the side chains, right? 1, 2, 3, 4, 5, 6, 7. Right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. Right? So it's looking like, again, in this case, the horizontal's the main one. So 1, 2, 3, 4, 5, 6, 7, 8. So C8, 8 carbons long, which would normally be octane, right? But since it's an alkyne, we take off the ANE and add YNE. Okay, so don't forget that carbon-carbon single bonds, it's ANE, right? Double bonds, it's ENE. Triple bonds, it was originally INE, but they changed it somewhere along the way to make it YNE, to make it I don't know, easier to pronounce or something like that. But notice how it goes alphabetically by the vowels, right? AE, originally I, but it's Y. AEY as you go double, single, triple. So that was actually by design. So okay, so with that, so we're going to have to say where that alkyne starts, right? Just like we did with this one, right? You know, where on this chain is it? Okay, and then we have this guy here, right? That's a methyl group, 1 carbon long. This guy here, right? It's 3 carbons long, right? So it's propyl, but it's connected to the main chain through carbon 2, right? So it's a 2-propyl group. You could also call it an isopropyl. I like 2-propyl because it's a little bit more descriptive. With that, so but either one will work. Okay, just like this one here, the end of the chain, carbon 1 is the end of the chain that where the double bond is. In this case, the end of the chain is closest to the triple bond, right? So here he goes. So 1, 2, 3, 4, 5, 6, 7, 8, right? So in this case, the triple bond starts at carbon 1, right? The methyl group is hanging off of carbon 4. The 2-propyl group is off of carbon 5. Okay. Now for alkynes, we don't need to worry about sister trans, right? Because there's only 1 hydrogen hanging off of here. So by that, so we only have to worry about that with alkenes. Okay. So which comes first, methyl or propyl? In this case, it's methyl because for alphabetically, so it becomes 4 methyl, 5 2-propyl, okay, 1 octyne. Okay, so we have a main chain of 8 long. There's a triple bond in it, right? Where is it at? It starts at carbon 1. Okay, we also have a 2-propyl group here. Where does that connect to the main chain? It connects through carbon 5. We also have a methyl group, right? Where does that connect to the main chain? It connects through carbon 4. So here's your name. There you go. Okay, so we're gonna have to do E and Z, right? To put that. So, okay, so this is similar to cis and trans, right? But you can have fewer than 2 hydrogens on it. Okay, so the way you do this is you have to slice these guys in half. Okay, and then you have to do the priorities of this side, that side, versus this side. Okay, but we're going to use the same priority rules as we did for R and S. So we're going to look at which is going to be the higher. Right, you could sort of think of this one. You know, with R and S we did 1, 2, 3, 4. Right, you can in this case what's priority 1 versus priority 2, which has the higher priority over the other. So I usually use high-low, but that's okay. So here we go, chlorine. Right, so you're going to look on this side, chlorine versus nitrogen. Right, so with that, so in this case, chlorine is heavier than nitrogen. So this is going to get this is higher priority than this. Okay? So we just sort of ignore this side and say high-low, right? So in this case, this is high because chlorine is heavier than nitrogen. Okay, so on this side, right, we have a CH2, right? CH2, CH2, H2, CH2, CH3, excuse me. Okay, so we look here, right, versus here, right? So that is, so they're both carbons, right? So we have to look at the bonds. So two carbon-carbon bonds, 2 carbon hydrogens, right? here we go. For this one, again, it's 2 carbon-carbon bonds, 2 carbon hydrogens, right? So there's a tie, so we need to go one farther out, right? So we're going to look at this versus this. This one here, right? Again, there's 2 carbon-carbon bonds and 2 carbon hydrogen, right? But this one only has 1 carbon-carbon bond versus 3 carbon hydrogen, right? Since this has 2 carbon-carbon versus 1 carbon-carbon, right? Since they're the same, right? So they're the same weight, right? But this one has more of them. This is going to be the higher. This side is going to be the higher priority than this one, so it's high-low. So you look at where the highs are, high, right? They're on the same side, so on Z's same side, right? So this is Z. Okay, so again, we have to cut this in half, right? So we look here versus here, right? So that's the CH2, right? So we have hydrogen versus carbon, right? So this is going to be high. This is going to be low. Okay, so now we look on this side, right? So this is, again, CH3 versus CH2, right? So that one there, they're both carbons, right? So we have to look at the bonds, right? So this is 1 carbon-carbon bond, right there. 3 carbon hydrogen, right? This one is 2 carbon-carbon, right? Versus 2 carbon hydrogen, right? So with that, so 2, right? So they're both, the heaviest bond is carbon-carbon, but this has 2, this one has 1, so this is going to be the high. Now don't be tempted to say, well, that's definitely going to be the high because this has it's longer and it has the chlorine. Remember, that's a common mistake, right? Just go through the same progressions each time. Don't try to shortcut this thing. Okay? So with that, so high is up here, right? And low is down here, right? So high is, they're on opposite ends, opposite sides, so this one ends up being E. Okay? Not too bad. Okay, so mechanisms. Okay, so with that, so these are the 3 potential mechanisms that you're going to have. Okay, you're only going to get one on the exam, right? I don't have time to give you all 3. So with that, but they're all very similar to this. Okay, so with that, so but we'll work through one of them. So, okay, but these are the 3: adding either bromine or chlorine to an alkene, adding bromine or chlorine to an alkene in the presence of water. So you're going to make the cyanohydrin. Not the cyanohydrin. That's another thing. With that, so with that, or you're going to add HBr or HCl to an alkyne. Right? They're all going to be very similar mechanisms, but you're going to get one of those. So, okay, so here it is. You're not going to have to predict the product. I'm going to give you what the product is, but you are going to have to draw the mechanism to account for this. Okay, so for the Br2, right, you have to think of this as BrBr, right? So with that, so the mechanism is, right, so this is going to attack here and push that away, okay, to give you, right? Now, right, so usually what happens, right, so I'm drawing the hydrogens here to make it a little easier to see. But notice how this only has 3 bonds, right, so there's going to be a plus charge here, so this is going to go on one side, right, to give a plus charge, right, plus Br minus, right? But here, right, we have a plus charge and we have a set of lone pairs, so that's going to attack here to make this nice resonance structure. Br minus. Okay, so with that, so you're going to right, so you need to make this resonance structure here. You have a plus charge, you have a set of lone pairs. This lone pairs is going to make a bond with this to this carbon here that's positively charged, but the positive charge up on the bromine, the bromonium ion. Okay, well, this thing, right, so this is stabilizing, so this is a way to stabilize that positive charge while this bromine comes in and before this comes in attack. So it's going to attack there to form that. Okay. Now if you did it with water in the presence of this, okay, instead of this, you would have water coming in and attack. But otherwise, the mechanism is exactly the same. Okay, so instead of the Br minus coming in and attack, if there was water here, the water would come in and attack that positive charge. Okay, and it's the OH is going to go on the side, on the higher numbered side, right? So this is a primary, right, because it only has one carbon. This is a secondary, right, because it has two carbons attached. So the OH is going to come on the higher numbered side, but you'd see that because of the because I'm going to give you the product. Okay, so the mechanisms are going to be very similar to this. Okay, so next up, the other mechanism you're going to see is one like this. It's going to be a hydride alkyl shift, and you'll know that it's happening because I'll say the product was unexpected. What happened? Stuff like that, and so you're going to be able to do stuff like that. So you'll know something's up. Okay, because notice how the hydrogen and the bromine, they're not adding on directly onto this either this carbon or this carbon part of the double bond. Right, the bromine is up here. So something's happened. Something's moved. And a good trick for this is to go ahead and draw on all the hydrogens. Okay. It's a little bit easier to see what's going on, right? So what's happened, right? So I'm going to draw it like this. Okay. This has come here and pushed this away. Oops. Let me draw this. So hydrogen, 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 right? The new hydrogen has come in and added here to leave the positive charge there. Okay, now, why did I put the hydrogen there and the positive charge there? Is that eventually, so what you're going to want is you're going to want that positive charge next to where your your bromine or chlorine or whatever it adds. Okay, so if the bromine's going to add here, you're going to want that positive charge there. Okay, because what ends up, you also made plus Br minus. Because what happens is this hydrogen shifts over there. If the positive charge is there, right, this is going to be too far to move. Okay. Because you end up with this, and then this is where the bromine attacks to give that. Okay, you're going to have an alkyl shift. Something shifted. Okay, and it's either going to be an H in your molecule or an alkyl. Typically, it's a methyl group that shifts. Okay, and the driving force is the fact that this is a secondary carbocation. If you shift this over, you now get a tertiary, right? Because on this carbon there's 1, 2, 3 carbons attached to it, so it's tertiary versus secondary. Tertiary is going to be a lot more stable. Okay, it's going to be like you're going to know because it's not. You know this is going to happen, right? Because you're not. This Br doesn't add on either one of these carbons. Okay, it adds up here. So something's moved around. Okay, and you're also going to get. Well, here. I'll get to the synthesis one. So you are going to get some like this. Okay. Where you either need to fill in the product, okay, or you're going to need to tell me what the reagent is that does this transformation, okay, so like that. So for here, right, ozone, right, so don't forget there are some hydrogens here, okay. What does ozone do? It slices it in half, okay, and where there were carbon-carbon bonds, now there's carbon-oxygen bonds, right. So the easiest way to show this, to draw this, is like this. And that'd be perfectly acceptable. Where there was a carbon-carbon bond, now there's carbon-oxygen bonds. Okay, there you go. That's the easiest way to see this. Now for this one, right, HBr, right, this would actually be an excess. So with that, so what you're adding, right, we're adding to this to here, right, but the hydrogens are going to go here, right. The bromines are going to go there. right? Because in this case, right, this is gonna attack the bromine, or excuse me, attack the hydrogen, right, to leave a positive charge behind, and this is primary. That a primary carbocation is going to be really bad, but the secondary is not so bad. It's going to add once, you're going to leave a double bond, and so it's going to add again. Okay, and so you're going to end up with both of your bromines right here. They end up going on. Both of these bromines are going to go on the higher numbered side. Okay. Now for this one, right, osmium comes in and it adds hydrogens, or it adds OHs, but it adds it because it comes in like this, bang, it's going to add them on the same side. Like that. Okay. Now for this one, again, you're going to need to know this, right? So I included this, and I forgot to show you this before, right? So I've included this list of reactions, this big list. And what it's doing is it's saying, okay, here's the reagent that you need, okay? And then what's going on with the reaction, right? So for something like HX, right? So you add HX across the double bond, and the X goes on the carbon with the more substituted, higher number of these two. Okay, so you may want, this is actually probably the more important of the two sides, right? This is just to illustrate what's going on, but this is what's actually going on. This is what you need to know here, okay? Because when you're thinking about these reactions, you have to think, okay, what am I doing with these things? I'm taking a triple bond and I'm adding HBr to it. Okay, so you have to think about what that does, because I'm not going to give you these particular reactions or these particular chemicals. They're going to be more like this. Okay, but the chemistry is still the same. So you have to sort of understand the chemistry of what it's trying to do. Okay, so like this one here, right? So I'm taking a carbon-carbon double bond and adding an OH on it, right? HOH across it. Okay, but the OH is going on the higher numbered side, right? Because this is secondary, that was primary, right? Because this carbon has 2 carbons attached. This one only has 1. So what puts an OH on the higher numbered side? Well, it's the mercury acetate. Okay, H2O, H plus, and then I think it's sodium. That. Yep. Okay, this is the most important thing to put. That's what puts it here. Okay. Now here you go from a double bond to an epoxide. So what does that? You have to think back to your list. It's MCPBA. Okay. And here, right? So we're adding, right? We're adding a Cl and an OH across this. Okay. So with that, so it's a chlorohydrin. Sorry, the chlorohydrin. The right. So normally it would be HCl. Right, but since we're adding an OH on it as well, what's happened is we have HCl plus water. Okay. Okay. So like that. So you're going to need to know these. You're going to need to know these reactions. Okay. So like that. So okay. Because in the end, what we really want to do is we really want to do these design a synthesis. Okay. And so you're going to get one of each, right? So one where I give you, there's going to be one here where I give you what the carbons look like. Okay, you have to start for this one specifically. And then another one where I give you a list and you have to pick the products from the list. Okay, pick the carbons from the list to generate this. Okay, so the way that you usually want to approach this is to say, okay, just don't worry about this part here. Take a look at this. Okay, and notice here I'm going to draw on these hydrogens here. Okay, and so what makes? So you have to ask what makes a cis carbon-carbon double bond. Okay, that's what you really need to ask yourself. The functional group that gets put in. And you have to go back to your list, and what the reaction is you take a triple bond, okay, and then you react it with H2 Lindlar. That makes That makes the cis double bond. Okay, so what does this need to look like? Right, we know what the last step is going to be. It's H2 Lindlar. Okay, it has to look like, right, because there's CH3s here. It has to look like this in order for this last step to put that functional group in. So then the question is, how do we build this? Okay, because usually what happens is the first part of the reaction, or first part of the synthesis, is going to be just getting this carbon skeleton put together, and then you put in the functional group. That's usually how these ends up working. Okay, and so, right, so you have a 1, 2, 3, 4 carbon piece, right? So notice how this triple bond looks a whole lot like this triple bond, right? And this triple bond, right? But here you only have 2 carbons and 3 carbons, right? We need 4 carbons. Okay, but if you notice, this right here looks a lot like that there. Okay, so but that, so we have a 3 carbon piece here, and ooh, hey, we have 3 carbons here with a double bond in it. Okay, so all we need to do is add this piece to it. Okay, so how do we make carbon-carbon bonds with the triple bond? Right, so we go like this. So we start off with this. Okay, we add sodium amide. And again, this is on your list of reactions, right? That's going to rip away that hydrogen to give you this. Okay, then you have to pick. Okay, so this is all ready to go, and this can go in and attack a bromide, right, to add carbons on there, right? So we have a 1, 2, we have three carbons. Our final product's going to have 4, right? So we need a 1 carbon piece. You look on here. Is there a 1 carbon piece? Yep, there is. It's right here. Okay, so if we add that, right, this is going to come in and attack, displace this to give you that product there. So here's the synthesis. The second half of the reaction is putting in this functional group. In this case, it's this cis double bond, right? And then the first half of the synthesis is going to be just getting that carbon skeleton put together. Okay, but you're going to need to know those. You're going to need to know those reactions. Okay. Okay, so here's another one, right? So here we go. Okay. There's actually a couple of different ways you can do this, but we'll go through one of these, right? So how do you make a ketone? So with this, so right, so we have one. So one of the things, especially if I give you the carbons, make sure that there's the right amount of carbons, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so there's 6 carbons here, right? There's 6 carbons here. So we're probably good to go. We don't have to add carbons. We don't have to remove carbons. It's just a good, quick check. Okay. So how do we make a ketone? Okay. Well, there's, right, so we could do, say, you know, we could do like ozonolysis, right? Right, but notice if you do that, you're going to break away part of the carbons. We probably have all the carbons what we need. Okay, so another way that we could do it is to do something like the BH3 or mercury sulfate, mercury oxymercuration, or hydroboration, and that converts that into that. Okay, this puts the oxygen on the less substituted side. This puts it on the more substituted side. So if we want to do this, okay, what we would want to do, right, is to do one of those, right? But here, right, so if you did the molecule like this, like that, right, if we put the triple bond there, right, if we put it there, right, they're both secondary, and you'll get a mixture of the two. Okay, if we put it here, notice how we have a secondary carbon versus a primary carbon. Right, now we can get selectivity. Okay, so if we put that, right, so we want to put the ketone on the more substituted side, right? So secondary versus primary, right? So that means that we're going to have to do this mercury sulfate, like that. Okay, so then the question becomes, okay, so just irrespective of this, right? So this is what we would need to do. If we want to do that step there, we would need to do, we would want to do that there, okay? So, okay, so how do we make a double bond into a triple bond? Okay, so this is the step, right? So how do we make a triple bond? Well, the way that you do that is you take something like this, okay, and you treat it with KOH, or sodium hydroxide, you treat it with base, okay? So what we're doing is we're making basically two double bonds, okay? So how do you make a double bond, right? You have a hydrogen on one side and you have a leaving group on the other. You treat it with base, and that rips it away, that collapses down, kicks off the bromine. With the triple bond, you just do it twice. Now after that, more base, you grab that collapses down, kicks off the bromine, okay? So how do we go here, right? So then we say, okay, well, this is what we need to do, okay? Well, how do we go from here to here? Well, how do we put bromines on both sides of a double bond? Well, we just add Br2. Okay. There you go. Now, the other question becomes that there's another way that you could actually do this. Okay. Right. So we need to put an oxygen there. So how do we put the oxygen on the more substituted side? We do the mercury. Well, you could do mercury sulfate, mercury acetate, doesn't matter. H plus. Right? And then you hit it with some sort of oxidant. So, so Des-Martin. Or chromium trioxide, or potassium permanganate. That would also work too. So there's more than one way to deal with these things, okay? Stuff like that, and all of them are equally valid, okay? Stuff like that. So I don't care which one, okay? So, so learn your reactions, right? So if you learn a foreign language, right, the first thing you got to do is you got to learn the words, right? So these are your words before, and then you can start building sentences, and these are your sentences. Okay, so start working on these reactions, right? There's a big list in their review slides, and good luck.